everyone, I'm Bruno from MOVEdot, and welcome to the 5th episode of our VI-CarRealTime tutorial series. Today, we'll continue right from where we left off in the previous episode, when we were analyzing ride performance. We were studying metrics connected to driver comfort, and using that to define the ideal range of settings for our dampers, the one that would optimize the ride comfort for our car. Our next task will be to go beyond just comfort. We'll investigate ride tests with the goal of understanding how different damper settings will influence the performance of our car. And for that, we'll use virtual post-rig testing to analyze metrics such as tire vertical load variation and ride height variation to understand compromises between tire performance and aerodynamics performance. With all of these results combined, we'll be able to decisively define the new baseline settings for our dampers, the one that will give us the best compromise between all of these different aspects.
Let's begin by loading our track car tutorial session from the file menu to keep working with it. Today's studies will be conducted on a virtual post rig, which is available as an event we can configure in VI-CarRealTime. In its essence, a basic 4-post rig is an indoor machine able to displace pads below the tires of a vehicle up and down. A test is conducted by positioning a car over the machine so that each wheel rests on a vertical actuator. These actuators are also able to measure the vertical load, and by applying different movement patterns to them, we can observe how load variation happens at the contact patches in transient situations. 7-post rigs also attach the car's chassis to the machine, allowing for the emulation of vertical forces and inertia effects. With proper instrumentation, it's possible to directly measure ride height variation, as well as the relative displacement, accelerations, and forces between the suspension components during the tests. Engineers can then use all of that information to optimize the vehicle's suspension. Being able to simulate this test in a virtual environment not only means a big advantage in terms of cost and time savings, but it also means we can start refining the project according to ride performance, even before creating a physical prototype, streamlining the whole vehicle design process. We will investigate the effect of different damping levels on tire load variation and ride height stability as we perform a frequency sweep in heave to emulate bumps on the road. Our goals are to identify the damping levels that cause the tire load to remain as stable as possible during the sweep, indicating a potential for great mechanical grip, and that will keep the chassis at a more steady height, ensuring predictable aerodynamic performance. Since we're using a heave sweep in a wide range of different frequencies, we are creating a generic base setup for the car that should perform well in many different tracks. When tuning for a specific track though, we could focus only on the frequencies that would be more relevant to it. Let's start by setting up the test that we will use to investigate the heave frequency sweep. In test mode, browse the bookshelf looking for the VI Test Rig Event folder. Right-click the 7-post rig and add it to a new fingerprint with the track car. Select it in the tree view to configure its settings. Set end time to 100 seconds, because we can run very long and precise tests, as our virtual dampers are not configured to behave differently with heat. Leave analysis type as analytic. Set the wheel actuator mode to contact patch, meaning the tires will only rest over the posts. The other alternative allows us to fix the actuators to the wheel hubs instead. The excitation mode for this test will be heave, and the function type will be a sweep. Set peak velocity to 100 millimeters per second, initial sweep frequency to 0.5 Hz, and the final frequency to 15 Hz. Let's select the No Aerodynamics mode and set No Body Fix. Despite VI-CarRealTime being able to simulate 7-post rigs, by not activating the aerodynamic mode and not fixing the body to the machine, we are effectively doing a 4-post rig simulation, as only the actuators under each of the 4 tires will act on the car. For the solver settings, change the output time step to 0.002 and run the simulation. We will now set up an investigation where the car will perform this test with the selection of dampers options. Based on experience, we can define the initial range of damping ratio we want to cover. That will likely include the optimal damping for load variation and the optimal damping for height stability. These new dampers are ready to use, with no need for the scaling factors we applied to our original components. Therefore, let's head over to Build Mode and, within each suspension subsystem, open the Damper tab and change the scaling factors to 1.0. Our goal for the next investigation is to identify the best performing option among the ones we created, taking into account the compromise between these two performance aspects to use as our new baseline dampers. We will use a series of custom scripts for both investigations. So go ahead and download the files for episode 5 from the video's description, unpack it, and drag both folders to the same location where you're keeping the ones that were provided earlier in the series that should be located beside our database. Once the simulation is ready, let's head over to investigation mode. Once here, find the new event in the bookshelf. Right-click it and add to a new investigation. Select it in the tree view to set up its settings. Let's promote the following two candidate parameters into the factors that will be varied throughout the investigation. The front suspension's property file for the dampers, which is referred to as property URI, and the rear dampers property file too. Make sure to add them to group 1 as they will vary in pairs. The way this parameter will vary is different to the ones we used previously in the series. Instead of splitting a range in equal intervals, we will be selecting a string of files in the values field. We will keep the original damper in the investigation, so don't delete the original address from there. Let's click the Browse button and navigate to the Custom Dampers folder we added to the same location where your scripts folder is. Here, you will find our new dampers property files. Select the first of the front dampers, the one that ends with the number 3, and open it. It now shows in the string after the original one. Browse again and add front damper number 4. And keep doing this process until all remaining front dampers are added to the string, up until file number 13. Now, let's do the same for the rear damper property factor, by adding its own corresponding files to its values string. Keep the original one there and add the new files in order, from number 3 to 13. Investigating the effects of different property files as factors means we can have radically different behaving components being tested and compared at once. We will be looking at how these two factors affect 9 responses. So head to the responses box and add 9 items. The first group of 4 responses focus on the intensity of the tire load and ride height variation throughout the test. Select the first one and change its name to Load F, as this one will indicate how much the front tire load will vary in the sweep by looking at peak values. Set its function to Custom Computed Value, and for the output channel, browse for the Tire Forces Normal channel for the front left wheel. We will use one of the custom Python scripts provided earlier in the video because we want to observe how tire load varies in relation to frequency instead of time. Navigate to the scripts folder and select postrig fftmax.py. Also, know that we will be applying this very same processing script for some of the remaining responses. because the required mathematical processing is the same, but we will be normalizing their output data so that we can more easily compare them. And doing that requires a specific operation for each of them, which is included in the script too. We can add more parameters to be used by the script in the optional function parameter field, effectively allowing the same script to output different data according to specific needs. For this first response, this normalizing value is the one on screen. Now, select the second one and change its name to load R, as it indicates the rear tire's load variation. Set its function to custom computed value. For the output channel, browse for the tire normal force channel for the rear left and enable it. Browse for the post-rig FFT max script. And set the optional function parameter value to this one. Select the third response from the list and change its name to ride height F. This one will indicate the intensity of the ride height variation on the front axle throughout the test. Set the function to custom computed value. Browse for the ride height front left output channel and enable it. For the optional function parameter value, copy the value on screen now. And select the same post-rig FFT max script. Then select the fourth response and change its name to ride height R. Set its function to custom computed value. For the output channel, browse for ride height rear and enable it. Set the optional function parameter value to this one and select the post-rig FFT max custom script. The next four responses will quantify how much the factors affect the same parameters by displaying RMS values, which are an indication of the oscillation of the parameter over the entire range of frequencies. Head to the response list and select the next one. Call it RMS normal F. Set its function to custom computed value. Browse for the front left normal output channel and enable it. But for the remaining responses, we will browse for another custom Python script, the post-rig FFT RMS file. And for this response, use this optional value. Now, select response number 6 and change its name to RMS normal R. Set its function to custom computed value. For the output channel, browse for the rear left normal and enable it. Browse for the post-rig FFT RMS script. And set the optional function parameter value to this. Select the response 7 and name it RMSRHF. Set the function to custom computed value. Browse for the ride height front left output channel and enable. For the optional function parameter value, use this. And select the same post-rig FFT RMS script. Select the 8th response and change its name to RMSRHR. Set its function to custom computed value. Browse for ride height rear, enable it. Set the optional function parameter value to the one on screen. And select the post-rig FFT RMS custom script. The RMS responses, max tire load, and ride height variation are a lot of data to consider at once. And on top of that, a solution that improves some of them may do the opposite for the others, making the interpretation of the results not very straightforward. Situations like this are common also in real post-rig tests. And to deal with them, we can create a performance index that correlates all of the results into a single and easy-to-read metric. We created one to evaluate this specific scenario, and we will add it to the response list. Select the new response and name it Performance Index. Set its function to custom computed value. Browse for the following 4 output channels, in the order shown on screen. And for the custom Python script, look for the post-rig performance index file. What the script does is, it normalizes each parameter, scales them in terms of importance, according to our experience and expectations for this application, and combines them into a single value, which is the performance index itself. Of course, this performance index is tailored to the current investigation. It will favor more mechanical grip, since our car does not rely heavily on aerodynamics. Therefore, this file will not generate significant results if applied to a different database. But the file structure can be used as a reference for you to build your own indexes in the future. Select Full Factorial Simulation Type and set the mode to Inherited from Event. Name the output folder as Post-Rig. This concludes this investigation setup, and we're ready to save it. Save the session, and proceed to running the simulations. When the investigation is done, open its design space and results, and scroll down for us to observe the plots. For the group of intensity responses 1 to 4, what we ideally want is for the load and height to vary as little as possible during the sweep. So, the lower values on the plot indicate less variation and a better solution. Observe, though, how a solution that usually minimizes load variation won't do the same for ride height, and vice versa. If we look at the RMS responses group, 5th to 8, again, the lower the value, the better, as it indicates less overall variation to the metric during the test. It also suffers from the same effect where no solution is clearly the best for all responses at once. Having a performance index makes the analysis much more straightforward. We crafted this index so that the lowest the value, the better the solution is in managing the trade-offs between the different criteria. And by looking at it, we can clearly conclude that the best solution for our track car's ride, in terms of performance, are the dampers proposed for version 6. This solution provides a damping ratio of 0.7, which is in the expected range for a sports car. Highlighting it shows it tends to deliver low values for all of the other responses, despite not necessarily being clearly the best for many of them individually. Version 12 may look like a strong alternative at first. It represents the higher end of the damping ratios we established in the previous investigation, and it scores very well in all ride height related metrics. But it scores so poorly in tire load stability that its performance index is driven way up. On the other end, version 3 represents the lower end of the damping ratios we selected, performing fairly well in minimizing tire load RMS, but not as good everywhere else. For the sake of comparison, version 1 are the car's original dampers with no scaling factors applied to them, and its performance index still ranks very well, despite all the changes we made to the model so far. If we would plot the FFT of all of these 4 dampers for both the tire loads and ride height variations during the sweep, we would see these graphs that confirm version 6, in green, performs well all around when compared to the other ones. There is one last thing for us to do to make sure version 6 is an acceptable solution. We have to check how it does when faced against the results we got from the comfort investigation performed in the previous episode. Back then, we established an acceptable damping range in terms of scaling factors that roughly translates to the damping ratios on screen. Ideally, we want the damping ratio to be within 0.5 and 1.4. It's even better if it doesn't go over 0.9. The damping ratio for version 6 is around 0.7, meaning that not only it's a great solution for high performance, but it's also well within the ideal range for comfort. All we have to do now is install the new dampers to the model. To do so, close the results report and go back to VI-CarRealTime. In investigation mode, right-click the last investigation in the fingerprint and select Apply Variant. Select version 6 in the prompt and confirm. The new dampers are now installed, and we can head back to build mode to note the suspension subsystems were modified and are highlighted. Save all of the model to update the database. This is the finest change we made to the model in the series so far, and we don't expect huge lap time gains from it in a specific track. In fact, even if it would be slightly slower at the track we've been testing at, we expect it to serve as a better baseline setup for general road courses. We can now open the file menu and save the session. In this episode, we concluded our series of ride tests, and we now have optimized dampers for our track car. We did this by studying and running post-rig tests, performing complex investigations based on varying property files, simplifying a complex analysis by using a performance index, and cross-referencing performance and comfort ride data. With the changes we made, we improved the track car's ride and made sure it remains at satisfactory comfort levels, indicating higher performing and a more enjoyable car. In the next episode, we will continue to develop our car by studying how to tune suspension kinematics. I'll talk to you soon.